Then we can move on to our water molecule. So as we know, our water molecule is made out of 2 hydrogens and 1 oxygen. So we have a hydrogen plus an oxygen plus another hydrogen. So how many valence electrons does hydrogen have? Only 1, right? Because it only has 1 electron at all. Okay, so both of our hydrogens, we draw in 1 electron because it only has 1 valence electron. How many does oxygen have? 6. Okay, so again, we start by writing or drawing 1 electron on each side of the oxygen before we start to pair them up. So now there's 4 electrons, 5, 6. Okay, so we'll see why it is important to draw 1 on each side before we start pairing them up. We'll do that now. Yes. What do you mean? This electron? Okay, so you want to put 1 here.
I was asking if we can do it.
Okay, so do you mean draw it like this? Okay, so no. You are not allowed to do, hey guys, important now, you are not allowed to draw the oxygen like this. So with the single electrons on opposite sides, you're not allowed to do that. They must be on the same side, and we'll see why now. Yes.
Sorry, so for instance, for the electron that's facing towards the edge, does it matter, like, if it's, like, you know, on the top or at the bottom?
No, it doesn't matter that much, as long as it's not paired up like these two are. Okay, so what is happening here? This electron is going to be shared. These 2 electrons are going to be shared. Yes. Thank you very much. Okay, and these 2 electrons will be shared. So the oxygen will be sharing with 2 hydrogens. This will result in a structure that looks like this. Okay, so we see we have 2 paired electrons from our oxygen, 1 on the top and 1 on the right. Okay, are paired electrons. So they must stay that way when we draw the final Lewis structure. Then here we have our hydrogen's electron and our oxygen's electron that is shared between the hydrogen and the oxygen. And the same here, we have the electrons that are shared between the hydrogen and the oxygen. Okay, so this is very important because water's molecule is angular. It's not a straight linear molecule like this, right? Okay, it is angled like this. Okay, this is very, very important. That's why I say top, right, bottom, left. Okay, and you go clockwise or anti-clockwise. Top, right, bottom, left. And then you pair up your electrons. Okay, so you guys remember when we draw these electron configuration, first there must be an electron in the orbital, and then you can pair it up, and when we get to our 2p orbitals, there must be 1 electron in each orbital before we can pair them up, right? Same here, there must be 1 electron on each side before we can start pairing them up. Okay, now we can draw our energy level representation. So this one is orbitals for hydrogen, and this one is for hydrogen, this one is for oxygen. So we have hydrogen, hydrogen, and then oxygen. So hydrogen has 1 valence electron. So we draw 1 electron in each orbital of our 1s orbitals. Okay, We said oxygen has 6 valence electrons, so it's 1, 2, 3, 4, 5, 6. So now we can see where the overlap in orbitals will take place. So we will have an overlap in our second 2p orbital and an overlap in our third 2p orbital. Okay, so why we use this example is to show you that 1s orbitals can overlap with 2p orbitals. So it doesn't matter what energy level we're in, and it also doesn't matter which type of orbital we have. And once again, we just see here, we can have our s orbital that overlaps with a p orbital. And remember, our p orbitals are the teardrop shaped, while the s orbitals are round. Okay, so once again, you must be able to draw the Lewis structure, the energy level representation, but not the orbital representation. They can give you any molecule and ask you to draw the Lewis diagram or the energy level representation. Okay. So, next up, we have some more drawings of Lewis diagrams. So, the next one we have is hydrogen chloride. So, do you guys want to do these as examples? How do you guys feel about Lewis diagrams? Do you think you will be able to draw one?
No.
Okay, who says no? Most of you. Okay, so let's do... wait, you can't do this. I need to show you. Okay, so hydrogen has 1 valence electron. So hydrogen with the 1 valence electron. Okay, you can draw this valence electron on the top as well, as long as there is only 1. And then we add chlorine. Yes.
Can it be a circle there?
Yes, the dots and crosses can switch around as long as one is dots and one is crosses. Okay, I draw the hydrogen with crosses because chlorine has 7 valence electrons, so I don't want to draw 7 crosses. I'd rather draw 7 dots. But it's only like you want to. Okay, so chlorine 1, 2, 3, 4, 5, 6, 7. We can see that these are the 2 electrons that will be shared. So at the end, we get our hydrogen sharing 2 electron with chlorine, and chlorine having the same valence electrons around him. Okay.
How do you know if the structure differs?
Okay, so that is why we follow our rule. Okay, that's why we do the top, left, bottom, right. Top, left, bottom, right. 1 electron in each before we start pairing them up. Okay, we'll see that now with the next. We'll see that again with the last example here. Yes.
Ma'am, how would we represent, something's electrons around it if it has more than 8 electrons?
Okay, we are talking about our valence electrons, right?
Yeah.
Okay, so this is, we only have space to draw 8 electrons. So now I told you guys about the other method of determining the amount of valence electrons, but you'll see when we do ionic bonding, you're going to have to draw the Lewis diagram with iodine. Okay, and if we have 53 minus 36, we get to 17. There's no space for 17 valence electrons, right? Okay, so we look in group number 13, they have 3 valence electrons. In group number 14, they have 4. Group number 15, they have 5. In group number 16, they have 6. In group number 17, they have 7. Okay? So it's your group number minus 10 tells you the amount of valence electrons. Okay? So that you can use that to get iodine as 7. So you will draw iodine with 7 valence electrons. Does that answer your question?
Yes, it is.
Okay. So oxygen. Oxygen has 6 valence electrons and 2 are unpaired. So oxygen with 6. So 1, 2, 3, 4, 5, 6. We add another oxygen. 1, 2, 3, 4, 5, 6. Now we see each of our oxygens have 1 unpaired electron. Okay, now they have 2 unpaired electrons is what I meant to say. Okay, so 2 lonely electrons here and 2 lonely electrons here. So what is going to happen in our oxygen is these 2 electrons will be shared and these 2 electrons will be shared. So this is going to give us a Lewis structure that looks a little different. So we have the oxygens, and now they share 2 pairs of electrons.
For electrons to be shared, like must they be close to one another?
Yes, the orbitals overlap. As we saw in this one, the orbitals overlap here.
The single ones can be on the other side, the other ones are.
Yes, okay, so this is just a simple representation because our p orbitals look very much different than this. Okay, so it would be more something like this. Okay, so I know it's difficult, but don't think too much about this orbital representation. That's why you don't have to draw it, because it gets too complicated too quickly. But I think they will be shared something like this. Okay, so then there is the points that they are shared. Okay, so if we have the center of our 2 atoms here, and this is our 2p orbitals, or 2p orbitals, and the other atoms p orbitals, and then they are shared like this. It's something like that, but it's not important for you to know. Okay.
In your structure, you draw like anti-clockwise.
You can do clockwise or anti-clockwise, it doesn't matter.
My side's
Okay, so your alone electrons are over here.
no, one is this. They are both that side.
Both here. Oh, so you mean these 2 look exactly the same?
Yes.
Okay, yeah, that is also fine. Just make sure you draw from the one alone electron to the other alone electron. Okay.
Like she was not she was asking them, but she.
Oh, okay. Oh, sorry. Yeah.
To put in those arrows.
No, you don't have to put in those arrows. Those arrows are for me to show you guys where it's going. Okay, so this is now a different type of Lewis structure. So our first oxygen has these 2 electrons that is being shared, so we write them below each other. Only if there's more than 1 electron pair that is being shared. So for this oxygen, we have these 2 electrons that are shared, so we write them like this. Okay, so this forms one covalent bond, and this forms another covalent bond. Okay, now to draw in our other electrons over here, right? As we know, electrons are negative and they will repel one another because negative stuff repels other negative stuff. Okay, so these 4 electrons here are going to push these 4 pairs of electrons as far away as possible, while these 2 also push each other as far away as possible. So then we are going to get our electron pairs here at an angle on our oxygen. Okay? This is a little bit more, what do we call it? Grade 11 work, I mean. Right? But we're showing you now how something like a double bond exists. if we draw the Cooper structure for this, for oxygen, right, it would be an oxygen with a double bond and an oxygen. So one line in our Cooper notation represents a pair of electrons that is shared. So in our first molecule, it would just be H with a line chlorine. Okay, because one stripe represents one covalent bond. So it's one pair of electrons that is shared. Now we have two pairs of electrons that are shared, so we have two lines. Okay, then our next one is our nitrogen molecule. So nitrogen has 5 valence electrons. So we go 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5. So these 2 electrons will be shared, these 2 electrons will be shared, and the last ones will be shared as well. So now instead of only 2 pairs being shared, we're going to have 3 pairs that is being shared. Okay, so this will be nitrogen and nitrogen with 1, 2, 3 electrons here and 1, 2, 3 electrons there. Now, if these 6 electrons in the middle push away are 2 paired electrons, right? Where are they going to end up? Not at the angles, because remember we only have 2. We only have 1 pair, so they will be at the sides, the farthest away they can be. So we will have our paired electrons on the sides like this. And for this one, our Cooper notation would be written with 3 lines. 1, 2, 3. Because there are 3 pairs of electrons being shared. Okay. Then we get to carbon dioxide. So we have carbon plus 2 oxygens. Carbon has how many valence electrons? 4. 1, 2, 3, 4. Oxygen, we said, has 6. So it's 1, 2, 3, 4, 5, 6. Okay, and 6 on the other side as well. 1, 2, 3, 4, 5, 6. So we have 1, 2 unpaired electrons. We have 1, 2, 3, 4 unpaired electrons from carbon and another 1, 2 unpaired electrons from oxygen. So what do you guys think is going to happen here? Yes, so we have these electrons being shared and we have these electrons being shared. So we will get 2 double bonds. So we will once again have our oxygen with the 2 electrons that it shares with the carbon, and the carbon sharing the other 2 electrons with the other oxygen. And now we have the electrons, our paired electrons from oxygen being pushed away on the angle of the oxygens. Okay, so do you guys have any idea what the Cooper structure for this is going to look like?
O, 2 lines, C, 2 lines.
Yes. O with a double bond to the carbon with another double bond to the other O, the other oxygen atom. Okay, and lastly we have our ammonia molecule, NH3. So here we have our nitrogen. I'm going to draw this one a little differently for space. Nitrogen has 5 valence electrons. So we have 1, 2, 3, 4, 5. And then it bonds with 3 hydrogens. So we have hydrogen and hydrogen and hydrogen. We have 3 unpaired electrons with nitrogen, and each of the hydrogens have 1 unpaired electron. So it's easy to see how these will be shared. Right?
Can you write NH with 3 electrons and 1, 2, 3? How does it physical?
Okay, what do you mean? Just ask that again.
Usually we say N with the number of electrons around plus H with the number of electrons around, or must we draw it like yours?
No, you don't have to draw it like mine. We'll see later on where there's space. You can draw it like this, for example. Okay, and then we plus 3 hydrogens with their 1 electron. Is that what you mean? Okay, so you can do it like this, or you can have the plus H with the 1 electron. Okay, let me just plus H with the 1 electron plus H with the 1 electron plus H with the 1 electron. Is that what you mean? Okay, you can draw that like that as well. Am I answering your question? Okay, let me look at what you're doing.
Means like you say like 1, 2, 3.
No. No. Yes, you must write it like that thing. Or with the 3 in front of the H. Because what you're saying there is that 1 hydrogen has 3 electrons, and that's just not true. Okay, so she asked if you can draw the 3 hydrogens like this, but you can't because you're showing 1 hydrogen that has 3 electrons. Okay, and that's not right. Okay, so then we get our final molecule here. Just go back to blue. So we have our nitrogen. Important that your paired electron stays where you drew it first. So for me, that is on top. Then we have 1 hydrogen, another hydrogen, and our last hydrogen, all covalently bonded to our nitrogen. Okay, so for homework you are going to do A, B, C, D, and E on your own. Okay, important things I've seen the other grade 10s mess up is if we draw, for example, oxygen. I've seen you, if let's say we have oxygen plus another oxygen, for example, I've seen the electrons being written like this. Okay, not right. They must be either underneath one another, so either like this, or if they're on top at the bottom, then they can be next to one another. Okay? They all must be the same distance from your symbol. Okay, you can't draw it like this. That is wrong. Okay, and we must go top, right, left, bottom. That's the 4 places your electrons can be. Okay, you can't, the only way this is different is with these oxygen, with our electron pairs being repelled by our covalent bond. But if you draw your initial Lewis structure, you can't have it like this. Okay, not like this. It must be top, left, or well, top, right, bottom, and left. Okay, so before we get on to the homework, I want to do the next page of work with you as well.
So how would you write the copulatation of the molecule?
Okay, so we represent each covalent bond with a stripe, right? So it would be, I'm just going to draw it down here, NH, H, H.
Ma'am, in exams, do you draw this in pen or pencil?
Pen. You can draw it in pencil first, so if you make a mistake, you can erase it, but write your final answer in pen. Okay. No, please do it in your books. There's not enough space because I want you to write this part as well, where you add the molecules together. Okay. So giant covalent structures. Okay, so in certain non-metals, or atoms or molecules combine to form a three-dimensional network or lattice. You guys remember when I talked about a lattice? Okay, when we did the metal bonds. So do you remember when we talked about the lattice? Okay, so this is our lattice. It's a constant pattern that is being repeated. Okay, so these X's and O's can be molecules as well, or ions or atoms. Okay, so in some of our non-metals, the atoms or molecules are held together by a three-dimensional network or lattice. Lattice meaning a repeating pattern. Okay? And they are held together by strong covalent bonds, right? Because covalent bonds form between non-metals and more non-metals. So, for example, we have a diamond, right? What is a diamond made out of? Carbon. What is graphite made out of? Also carbon, okay? And you know those charcoals that some people sketch with? Okay, that's also made out of carbon. Okay? The lead in your pencils are not made out of lead. PB, it's not made out of lead. It's made out of carbon and clay. Okay. Yeah, there's a mixture of some type of clay in the lead of your pencils. Clay is mostly, I'm not sure, sand and water. I would be lying if I gave you an actual answer now. I'm not sure. Okay, so all of these stuffs is made out of the same element, right? And now we get to a new word called allotropes. Okay, so a diamond and graphite and the charcoal you write with are all allotropes, okay? Because they are from the same element, they are made out of the same element, but they have different physical properties, but they have the same chemical properties. Right, because our diamonds are very hard, but the lead in your pencil, for example, is not. The charcoal is not that hard, right? So it has a different physical property, but if you find something you can dissolve carbon in, right, both your diamond and your graphite will dissolve. Okay, because it has the same chemical properties. Different physical, but same chemical. Okay, so a diamond has, in each diamond, a carbon atom. Each of our carbon atoms is bonded to 4 other carbon atoms. We can see that in this sketch here.
Can you use a clear highlighter?
Okay, I'll use a other highlighter there. Okay, so we have 1 carbon atom here, and we can see that it's bonded to 1, 2, 3, 4 other carbon atoms, right? So that's what the first sentence tells us. So it's bonded by strong covalent bonds, okay, making diamonds the hardest material known. Okay, have you guys seen someone trying to break a diamond with a hammer? No. Have you not seen that? Okay, so they put it on this anvil type thing, this huge metal thing, and then they smash it with a hammer, and the diamond made an impression in the iron, and it did not break. Okay.
So then, can another diamond cut another diamond?
Yes, that's the only thing that can cut a diamond. If you go into For example, my fiance, after school, he was a tool maker for a year, and they have diamond cutting wheels. So, for example, if they try to cut tungsten, which is also a very hard metal, even though it is very, I can't remember the English word for it now, bros. No. Okay, but anyway, so they make diamond cutting wheels. Okay, so they take diamonds, which is in a fine powder, after they've cut out your nice diamond on your ring, and then they, I'm not sure how, but they put them on the edge of your cutting wheel. Like, you know, a grindstone, for example. You can get diamond grindstones as well, and then they use that to cut the very, very, very hard things. But yes, you can use a diamond to cut another diamond. Yes. Okay, so as all the valence electrons, okay, so all the valence electrons of each of the carbon atoms are used to form our covalent bonds, okay, there are no free electrons, which means no, they cannot. Okay? There are no free electrons that can conduct electricity. Okay, should just read the whole sentence together. So, no electricity will flow. Okay? If we connect a battery to a diamond, no electricity will flow because there's no free electrons to conduct the electricity.
So, ma'am, why will electricity like flow there if you have lemons?
Okay, because in lemon juice there are ions or free electrons, right? That means that electricity can actually flow. Okay.